So now we're going to look at how we might exploit target 6 if it was running on a different processor. And the processor that we're using is a RISC-V 64-bit version, and I don't actually have a RISC-V board. They're still fairly expensive, at least to get one that's powerful enough to run Linux. So I'm using an emulator called QEMU, and I have a Debian instance that I can install on it, and I will make a zip file of my setup available so that you could run this, but I'll warn you it's very sluggish. So I'm going to do this slightly out of order, just because jumping around in this disassembler while it's the processor's being emulated is a little painful. So let me start with a couple things. First of all, the RISC-V has two different names for each register. They're sort of the underlying name, where it's X something or F something, F or floating point, and there's X, which are general purpose registers, and there's X0, X1, X2, X3, and so forth. But then the way that different registers are used, they have different names, like aliases. And so one of the aliases is RA, which stands for return address. So if you think about the way the x86-64 calls functions, you use a call, and one of the things it does is it pushes on the stack the address of where you're supposed to return to. The RISC-V doesn't assume that you're going to be doing that with the stack. Instead, when you jump, you give it a register to put the return address of. So if we look down here at 105A4, that's the call to check password. It's doing a jump and link to this address, and the RA address, as soon as it gets to this location, the RA will have the address of the next instruction, which will be 105A8. And we'll see what some of the other registers are in a moment. I just want to make a note here. Remember when we did this before on the x86, what we wanted to eventually do is we did some setup, sticking a value in memory, and then we returned back to the call to open lock. And so that's at 105AC. So I'm going to go ahead and write down 105AC. That way, when we get to the point of writing this code, I'm not going to have to jump back here, because as you'll see, this interface is a little sluggish. So we're going to go look at check password now, and I'll explain a little bit more there about the operation of the stack. So let me go ahead and step over this statement. Let's do this again. View check password. What I did is I viewed it, but I didn't actually set a breakpoint there. And so I'm going to set one now. Hit the B, and it's going to take a second. Then I'm going to continue. And so now we should show there. It'll turn red in a second. And now I'm going to hit N to step over that. So now the stack pointer, it will be 48 less, 48 higher than it was when it first came into the routine. So instead of being at 470 over here, it's now at 440. And if I go to memory and I hit S to start viewing where the stack pointer is pointing to, we can see this. And so 440 here is the top of the stack frame for this routine, and it had been pointing to 470. So 470 is the bottom of the stack frame. So this B8 is not part of the stack frame. It really ends here at what would be 46F. So remember I said that the return address is stored in the RA register. Well, we still want it on the stack. So the first thing that gets done is it's stored on the stack. I'm going to hit N, and what we should see is that at 40 units past the top of the stack, which is right here, it has stored 105A8, which we saw was where check password normally returns to. Then the other thing it's going to do is save off this S0 register. Now, if you remember in the x86-64, the first thing you saw when it entered a routine was that it would push the BP register onto the stack, and then it would move the stack pointer into the BP register before adding something to the stack. Well, the ordering of this is a little odd. It's subtracting from the stack first, and then it's S0 is basically the RISC-V equivalent of the BP, so it points to the bottom of the stack frame, and so it saves the old SP or old S0, and then it adds that 48 back into the SP, storing it in the S0 register. So that means that S0 points to the bottom of the frame, so it's pointing to 470. So that's how we know now where to look for variables. We see right here it's zeroing out something at minus 20 S0, so there's probably a variable right there that's getting set to 0, and that might be a clue. But what I'm going to do is, remember, the place that was most fruitful was just after the second call to prompt. So I'm going to start scrolling down there. There was the first call to prompt, the JAL. And then right here is the second call to prompt, and I'm going to scroll down another 5, and while it's doing that, I'll start looking at these things. So after the second call to prompt in the x86-64 version, what it did is it stored the character exclamation point in this magical variable location, and in this case we're seeing that here. It just doesn't look like it because you see 33. GDB, for whatever reason, is disassembling constants as decimal instead of hex. There may be an option that I just didn't know to use, but 33 in decimal is 21 in hex, and so 33 is the exclamation point. So we're loading immediate. So we're loading the number 33 itself into the A4 register, and we're storing a byte. So the rightmost 8 bits of the A4 register are going into wherever the GP register points to, with 1936 subtracted from it. And so GP is sort of this. It stands for global pointer, and it usually points to sort of the bottom of all the program data, and then you can work backwards. You could index the actual code too relative to the GP if you wanted to. But it's something that gets set up when the program starts and just stays that way, and it makes it easier to refer to program data relative to this register rather than trying to figure out where it is relative to the instruction pointer or something like that. So this is a good thing for us to remember. We're probably going to want to have to do this instruction on the stack as we start exploiting the program. So the next thing we need to know is where on the stack is the buffer that we're going to be overflowing. And in order to figure that out, one thing we need to know is where do the values go when you call a function. And on the RISC-V, it's the A0 through A7 registers are the first 8 parameters to a function. So if you remember from the x86-64, prompt took 3 values, and the buffer was the third parameter. So if A0 is the first parameter and A1 is the second, A2 is the third. So we look back up here at where A2 gets a value before calling prompt, and we see it just gets whatever's in A5. So we back up and we see that A5 is S0 minus 40. So it's a pointer to the bottom of the stack minus 40. And so that's going to point to right here at this 448. So this is where our buffer is that overflows. So we're going to be, let's see, we want to be able to overflow all the way down to this 468. So that's 8, 16, 24, 32, 40. We're going to be entering in 40 bytes again, which is what we had to do the last time. The other thing that we need to know is, we go down a little further. Remember when we were doing this with the x86-64, the first time we put the buffer in, we put all these zeros in there, and that was messing up. It kept prompting us again for a password because it had a counter that's how many times you've tried the password, and we kept resetting that to 0. So no matter how many times we were to paste that in, it would just keep asking us again because we set it back to think that we hadn't entered in any passwords yet. And so what I can see here is it's loading a word from -20 S0. And if you remember when we were at the top of the check password function, we saw a call to 0 of S0 -20. And so that is likely where it was saying, number of tries, or whatever the variable name is, number of tries equals 0. And so now we see it's loading that word. It's adding an immediate value to it, which is 1. So it's saying basically load the variable into A5, and then says A5 equals A5 plus 1, and it stores it back. It loads it again, and then probably is doing some tests against it. It's copying it over into A4, and it's loading 2 into A5, which is probably going to do the is this less than 2 sort of thing. The reason I bring that up is we want to make sure that that this at -20 off of the S0 has a non-zero value. Maybe we put 10 in there or something. So that way, once we put in all our hex data, we're going to set this value to something that will immediately cause check password to return, and then it'll execute our code on the stack, and we can store the value we need and jump to the call to open lock. So this is actually, I think, all the information we need. I'm going to go ahead and put a little assembly program together so we can figure out what the bytes are that we need to stick into the stack to do this exploit. So let's call this T6RV for RISC-V.S. And remember the thing it was doing, it was loading an immediate value into A4 of 33. So we're just going to do that again, using basically the same instructions that it was executing. And we store that byte that was in A4 in -1936 indexed by the global pointer. So this is storing the exclamation point where open lock is going to look for it. And so then we want to jump to location 105 AC. And I think the jumps tend to be relative. I'm not 100% sure on that, but remember before what we had to do with the x86-64 is we had to put the address in a register, and I'm going to go ahead and just do that. So I'm going to load an immediate value into A4 again, because I've just stored A4. I don't need it anymore. I can reuse that register, and I'm going to put where we want to jump to. And I'm just going to enter it in hex, and I'd written it down as 105 AC. So this is the address in main where it calls open lock. And then I'm going to say jump and link register. So that's a different one, RA. And then I'm going to tell it to jump to A4. And there's a -0. There's I guess you can index it. And I could probably leave the -0 off, but I'm not. So this should store the exclamation point in this location and then jump to the call to open the lock. So let's hope this works. So the first step, that was the first step. The second step is I need to assemble this, and I'm going to store it in T6RV.O, and it's T6RV.S. Okay, and so it's assembled. Now what did the assembly code look like? We'll do an obj dump, and we'll tell it to disassemble T6RV.O. So these are the instructions that got assembled, and you can see the assembler actually did a little work. I guess the constant 105 AC was too big to be loaded immediate. So yeah, let's see, 5 AC is only 12 bits. And it's there's some things about loading 20 bits versus 12 bits. But anyway, it looks like it needs 2 instructions to really load that, but it's okay. The assembler took care of it for me. So these two, that at 8 and C, are the same as load immediate A4, 105 AC. I have those. What I'm going to do, I'm going to copy them into T6rv.txt. So this will be a working file for us. And let's work with this a little bit. So the first thing is that I've noticed that everything is in little endian order, which means that this number here, this 8-digit hex number, I'm going to have to enter these bytes backwards. So they're going to be 13, 07, 10, 02, and I'm going to go ahead and put the second one on the same line, 23, 88, E1, 86. The reason I'm putting them on the same line is that if I put 8 bytes across, that matches up the format over here of the memory layout, so that I can match things up closely. So that was the second one. So that I need to do the third one. It starts with 37, 07, 01, 00, and then 1B, 07, C7, 5A, and then the last one is E7, 00, 07, 00. Okay, so that's how these line up so far. Now, let's see. Let me just fill the rest of this out. Whoops. So we knew we were going to need 40 bytes. So the bottom of the stack frame has this at 468. It has the return address. Now, as we do this exploit, we want our return address to be this 3FFFFF448, because we want to jump to here where our stack code is. So right here, I'm going to just change this to be 48F4 FFFF3F and then zeros. So this is the location that it's going to jump to. And then the thing before that was the old stack frame pointer, and I'm going to leave that the way it was, which is 80 F4 FFFF 3F 000000. Okay, so we're almost done. The other thing we need to do is that location that was at GP minus 20 is that's going to be, all right, if this is GP minus 0, that's minus 8, that's minus 16, 17, 18, 19, 20. It's going to, okay, it's going to be right here, actually. Yeah, so I'm going to put a hex 10 in there. And, oh yeah, because this was minus 1, so that's minus 9, minus 17, 18, 19, 20, yeah. So this should set the number of times we've gone through the loop to 10, hex 10 or 16, so it won't prompt us again for a password. And I think this is actually all we need. So let me see if let me copy this the VI way instead of the terminal way. All right, and I'm going to join these things, and I'm going to exit out of here and cat this. I have had some cut and paste problems with this when I've been using VI from this virtual machine. So I'm going to copy this, and we're going to jump over here, and we're just going to give it a try. Let's see. I'm going to continue. I'm going to enable hex input, and I'm going to paste this in. And then I'm going to hold my breath as I hit enter. Hey, the unlock succeeded. Okay, so we successfully hacked a RISC-V program, and it really wasn't that different from the x86-64, other than just understanding what the different instructions did, how parameters are passed, and how the stack is managed. So I hope that was helpful.